The model isn't just a text-to-image generator, it's fine-tuned specifically for the task of editing. Architecturally, it conditions the diffusion denoising process on two things simultaneously: the clip text embedding of the instruction and an encoding of the original input image. This dual conditioning allows it to make localized, context-aware changes that respect the original image's composition rather than regenerating it from scratch. This is a paradigm shift from applying a global style to performing a specific instructed edit. For ML engineers, the holy grail is often specialization. How do we teach a massive generalized model about a new, specific concept? This is where Dreambooth comes in. The technique allows you to fine-tune a full text-to-image model, like Stable Diffusion, using just a handful of images of a specific subject, say your pet. You teach it to associate a rare, unique text token, like a scus dog, with this new concept. The drawback is that this process fine-tunes the entire model, resulting in a large, multi-gigabyte file for every single new concept. This is computationally expensive and difficult to scale. This is where LoRA, or low-rank adaptation, provides a brilliant solution. Instead of retraining all the model weights, LoRA freezes the massive pre-trained model and injects very small, trainable pairs of rank decomposition matrices into the transformer layers, specifically the cross-attention layers. All training happens only on these tiny new matrices. The result is a fine-tuned patch file that is often less than 20 megabytes, a 100-fold reduction in FIs. This makes it feasible to train, store, and swap thousands of different concepts on the fly, a game changer for production systems. So, we've journeyed from intelligent content removal to instruction-based editing, and finally to efficient model personalization with Dreambooth and LoRA. The trajectory is clear. We're moving towards ever-increasing levels of control and specificity. The next frontier is about composing complex scenes and exerting granular control over the output. Technologies like ControlNet are leading this charge. By conditioning the diffusion process on additional inputs like depth maps, human-posed celatins, or canny edge detection, developers can now precisely dictate the composition and structure of a generated image. This bridges the gap between the unpredictability of a text prompt and the explicit control of traditional CGI. Looking ahead, these principles are being extended to generate coherent video sequences and 3D assets. What this means for us as practitioners is that these AI tools are becoming less like black boxes and more like programmable visual synthesizers.